November 8, 1943. The heat pressed down on Henderson Field like a wet blanket. Lieutenant Commander Howard Vickery stood beside a 55-gallon drum of aviation fuel, watching a mechanic named Petty Officer James Carlo pump gasoline into a Grumman F-6F Hellcat. The drum looked clean from the outside, standard Navy issue, stenciled markings still legible. But Vickery knew better. He had seen 3 aircraft go down in the past month from engine failure, not from enemy fire, from fuel. Vickery was 34 years old, a chemical engineer from Pittsburgh who had joined the Navy in 1940. Before the war, he had worked for Gulf Oil, managing refinery operations. The Navy had assigned him to the Bureau of Aeronautics with a simple mandate: keep aircraft flying. But in the Pacific Theater, that mandate had become a nightmare. Fuel drums sat in open-air depots across hundreds of islands. Rain fell. Humidity climbed above 90%. Drums rusted from the inside. Water seeped through imperfect seals. And something else grew in the fuel: microbial colonies that thrived in the interface between gasoline and water, creating sludge that clogged fuel lines and carburetors. Vickery had arrived at Guadalcanal 3 days earlier. His orders came directly from Rear Admiral John McCain, commander of Task Force 38. McCain had lost patience. He told Vickery that contaminated fuel was grounding more aircraft than Japanese bullets. Fix it, or the air campaign would stall. Vickery knelt beside the drum and unscrewed the bung cap. He pulled out a glass jar and dipped it into the fuel. The liquid looked clear at first. Then he held it up to the sunlight. Tiny particles floated in suspension: rust flakes, water droplets, and something darker. He shook the jar gently. The particles swirled but did not dissolve. He opened the jar and smelled it. The gasoline odor was there, but underneath it, something organic and wrong. "Stop pumping," Vickery said. Carlo looked up, confused. "Sir, this drum just came off the Liberty ship yesterday. It's fresh." "Drain the tank," Vickery said. "This fuel is contaminated." Carlo's face went pale. He had already pumped 20 gallons into the Hellcat. If the aircraft had taken off, the pilot, Lieutenant Raymond Skinner, would have been at risk. Engine failure on takeoff meant a crash into the jungle or the sea. Vickery had read the incident reports. Pilots described engines that coughed, sputtered, and died. Some made it back to the field. Others did not. Vickery walked to the operations tent and found the fuel supply officer, Lieutenant Gordon Hayes. Hayes was a logistics man, not an engineer. He managed inventories and requisitions. He did not test fuel. That was not part of the system. "How many drums came off that Liberty ship?" Vickery asked. 400, Hayes said. "We've already distributed half of them to the forward strips." Vickery felt his stomach tighten. 200 drums of contaminated fuel were already in the supply chain. Aircraft across the island could be fueling from them right now. He needed to act fast. "I want every drum from that shipment quarantined," Vickery said. "No one touches them until I test them." Hayes hesitated. "Sir, we're running low on fuel. If I pull those drums, we might not have enough for tomorrow's strikes." "If you don't pull them, you won't have enough pilots," Vickery said. Hayes made the call. Within an hour, work crews were moving drums into a separate area. Vickery set up a field laboratory in a Quonset hut. He had brought basic testing equipment from Pearl Harbor: hydrometers, filter papers, centrifuge tubes, and reagents. He began testing samples from each drum. The results were worse than he expected. Out of 400 drums, 147 showed contamination. Water content ranged from trace amounts to several inches pooled at the bottom. Rust particles were present in nearly all of them, and in 32 drums he found microbial growth, stringy, dark colonies that formed mats in the fuel. The microbes were likely Cladosporium ricini, a fungus that could metabolize hydrocarbons. It thrived in the presence of water and created acidic byproducts that corroded metal and clogged filters. Vickery wrote a report and sent it up the chain, but he knew a report would not be enough. The problem was not limited to one shipment or one island. It was systemic. Fuel drums were being filled at refineries in California, loaded onto ships, transported across thousands of miles of ocean, and stored in tropical conditions with no quality control. The drums themselves were the weak point. They were made of steel with rolled seams and crimped bungs. Over time, the seams corroded, the bungs leaked, water entered, and once water was inside, the fuel was compromised. Vickery needed to redesign the entire system, but he was one man with no authority to change procurement standards or supply protocols. He needed allies. On November 15, 1943, Vickery flew to Espiritu Santo to meet with Captain Ernest Eller, the supply officer for the South Pacific area. Eller was a pragmatist. He cared about results, not bureaucracy. Vickery laid out the problem and proposed a solution. "We need three things," Vickery said. "First, portable filtration units that can clean fuel in the field. Second, sealed drum coatings that prevent internal corrosion. Third, trained personnel who can test fuel before it goes into aircraft." Eller listened. Then he asked the critical question, "How much will it cost?" Vickery had done the math. Portable filtration units would cost about $200 each. Drum coatings would add 50 cents per drum. Training programs would require instructors and materials. Total cost for the South Pacific area: roughly $500,000. "How much does it cost to replace a pilot?" Vickery asked. Eller nodded. "I'll get you the budget, but you need to prove it works." Vickery returned to Guadalcanal and began building a prototype filtration system. He used parts scavenged from damaged aircraft, fuel pumps, hydraulic lines, and mesh screens. He designed a two-stage filter. The first stage removed water and large particles using a coalescing filter. The second stage used activated charcoal to absorb dissolved contaminants. The entire unit fit on a wheeled cart and could process 200 gallons per hour. He tested it on the worst drum he could find, one with visible rust and microbial growth. He pumped the fuel through the filter and collected samples at the output. The filtered fuel was clear. Water content dropped to less than 0.01%. Particle count fell below detectable limits. He ran the fuel through a Pratt & Whitney R2800 engine on a test stand. The engine ran smoothly for 6 hours without a single misfire. Vickery wrote a technical manual and submitted it to the Bureau of Aeronautics. He included diagrams, parts lists, and operating procedures. Within 3 weeks, the Bureau approved the design and ordered 50 units to be manufactured and shipped to the Pacific. But filtration was only part of the solution. Vickery still needed to prevent contamination at the source. He contacted the refinery at Port Hueneme, California, where most of the Pacific fuel was being drummed. He spoke with the plant manager, a civilian named Robert Kemp. "Your drums are rusting from the inside," Vickery said. "We need an internal coating." Kemp was skeptical. "We've been using these drums for 20 years. Nobody's complained before." "Nobody was flying aircraft in 90% humidity before," Vickery said. "The Pacific is different." Kemp agreed to a trial. Vickery specified a phenolic resin coating that could be baked onto the interior of the drums. The coating was thin, flexible, and resistant to both gasoline and water. It added minimal weight and cost. Kemp coated 100 drums and shipped them to Guadalcanal. Vickery tracked those drums for 3 months. He tested them weekly. None showed internal corrosion. Water intrusion dropped to near zero. The coating worked. By February 1944, the Navy had adopted the coated drum as the new standard. Every drum shipped to the Pacific Theater received the phenolic lining. The change was invisible to most personnel, but it transformed the reliability of the fuel supply. The third element of Vickery's system was human. He needed trained fuel handlers who could detect contamination before it reached aircraft. He designed a rapid field test kit that fit in a small metal case. The kit included glass sample jars, filter papers, a hand-powered centrifuge, and color-coded reagents. A trained operator could test a drum in 5 minutes. Vickery wrote a training manual and established a school at Pearl Harbor. He recruited experienced mechanics and taught them fuel chemistry, contamination indicators, and testing procedures. The first class graduated 25 students. They were assigned to fuel depots across the Pacific: Guadalcanal, Espiritu Santo, Manus, Saipan, Guam, and Ulithi. Each graduate carried a field test kit and a filtration unit. They became the quality control gatekeepers. No fuel entered an aircraft without their approval. If a drum failed the test, it was filtered or discarded. The system was simple, but it required discipline. Vickery emphasized one rule: never assume fuel is clean. By April 1944, the contamination rate had dropped from 37% to less than 2%. Engine failure incidents attributed to fuel contamination fell by 90%. Pilots noticed the difference. Aircraft that had been temperamental became reliable. Sortie rates increased. The air campaign against Japanese-held islands intensified. Vickery's work was not glamorous. He did not fly combat missions. He did not sink ships or shoot down aircraft. But his system enabled those who did. Every Hellcat that took off from a carrier deck, every B-29 that bombed Tokyo, every transport that ferried supplies to forward bases, they all depended on clean fuel. In June 1944, Vickery was reassigned to the logistics staff of Admiral Chester Nimitz, Commander-in-Chief of the Pacific Fleet. Nimitz wanted Vickery to expand the fuel quality control system across the entire theater. Vickery traveled to every major base, from the Aleutians to the Philippines. He inspected depots, trained personnel, and standardized procedures. He wrote a comprehensive manual titled Aviation Fuel Quality Control in Tropical Environments. The manual became required reading for every fuel supply officer in the Navy. Vickery also worked with the Army Air Forces, which faced the same contamination problems. He met with Colonel Bernard Giles, Chief of Supply for the 20th Air Force. Giles was responsible for fueling the B-29 superfortresses, that were beginning to strike the Japanese home islands. The B-29 was a complex aircraft with temperamental engines. Contaminated fuel could cause catastrophic failure. Vickery provided Giles with filtration units, test kits, and training materials. He helped establish fuel quality control stations at Saipan, Tinian, and Guam, the three islands that served as bases for the B-29 campaign. The Army adopted Vickery's protocols and integrated them into their supply doctrine. By the summer of 1945, Vickery's system was operating across the entire Pacific theater. More than 500 filtration units were in service. Over 2,000 fuel handlers had been trained. Millions of gallons of fuel were being tested and filtered every month. The contamination rate had fallen below 1%. Engine failure incidents were rare. The impact on the air campaign was profound. In 1943, the Navy had struggled to maintain sortie rates above 60%. By 1945, sortie rates exceeded 90%. Aircraft availability improved. Maintenance hours decreased. Pilots trusted their engines. The sustained air operations that isolated Japanese garrisons, destroyed supply convoys, and cleared the skies for the final assault on Japan were made possible in part by clean fuel. Vickery did not receive a medal or public recognition during the war. His work was classified as part of the Navy's logistics operations. But within the supply community, he was known as the man who fixed the fuel problem. His methods were studied and replicated in other theaters. The Air Force adopted his protocols for operations in Europe. The British Royal Navy requested copies of his manuals. After the war, Vickery returned to civilian life. He rejoined Gulf Oil and eventually became vice president of refinery operations. He applied the lessons he had learned in the Pacific to commercial fuel production. He advocated for quality control standards, sealed storage systems, and contamination testing. His influence extended beyond the military. Vickery died in 1978 at the age of 69. His obituary in the Pittsburgh Post-Gazette mentioned his wartime service, but did not detail his contributions. The fuel quality control system he built remained in use for decades. The Navy's current fuel handling procedures still reflect principles he established in 1943 and 1944. The story of Howard Vickery is a reminder that wars are won not only by combat but by logistics. A pilot's courage means nothing if the engine fails on takeoff. A squadron's skill is useless if the aircraft cannot fly. Vickery understood that reliability is a weapon. He turned fuel from an invisible threat into a strategic asset. His work also illustrates the importance of technical expertise in military operations. Vickery was not a traditional warrior. He was an engineer who saw a problem and solved it. He used chemistry, physics, and industrial processes to save lives. He built systems that functioned across vast distances and harsh environments. He trained people to maintain those systems. And he did it all with limited resources and no precedent. The Pacific Theater in 1943 was a place of extremes: heat, humidity, distance, and danger. Fuel drums sat on coral atolls exposed to rain and salt spray. Water condensed inside the drums. Rust formed. Microbes grew. The fuel degraded, and pilots died. Vickery changed that. He introduced portable filtration units that could be operated by a single person. He developed drum coatings that prevented corrosion. He created field test kits that gave fuel handlers the tools to detect contamination. He wrote manuals that standardized procedures. He trained thousands of personnel. He built a system that worked. The filtration units were simple but effective. They used gravity and mechanical filters to separate water and particles from fuel. The units were robust enough to operate in field conditions. They required no electricity and minimal maintenance. A trained operator could set up a unit in 30 minutes and process hundreds of gallons per day. The drum coatings were equally important. The phenolic resin lining prevented rust and reduced water intrusion. The coating was applied at the refinery before the drums were filled. It added negligible cost but extended the usable life of the fuel. Drums that would have corroded in weeks remained clean for months. The field test kits gave fuel handlers the ability to make decisions on the spot. Instead of waiting for laboratory analysis, they could test a drum in minutes. The kits included visual indicators, filter papers that changed color in the presence of water, centrifuge tubes that separated particles, and reagents that detected microbial growth. The tests were simple enough for a mechanic with basic training to perform. Vickery's training program was rigorous. He did not just teach procedures, he taught the science behind the procedures. He explained why water contaminated fuel, how microbes grew, and what happened inside an engine when contaminated fuel was burned. He wanted his students to understand the problem, not just follow a checklist. The graduates of Vickery's program became evangelists for fuel quality. They took pride in their work. They saw themselves as the last line of defense between contaminated fuel and dead pilots. They tested every drum. They filtered suspicious fuel. They rejected shipments that did not meet standards. They built a culture of quality control. Vickery also worked to improve the supply chain upstream. He visited refineries and drumming facilities. He inspected loading procedures. He identified weak points where contamination could enter the system. He recommended changes, better seals, cleaner filling equipment, covered storage areas. Many of his recommendations were adopted. The Navy's logistics system in the Pacific was vast and complex. Fuel moved from refineries in California to ports like San Francisco and San Diego. It was loaded onto tankers and Liberty ships. It crossed thousands of miles of ocean. It was offloaded at forward bases, Guadalcanal, Espiritu Santo, Manus, Saipan, Guam, Ulithi, and dozens of smaller islands. It was stored in open-air depots. It was drummed, transported, and finally pumped into aircraft. At every step there was a risk of contamination. A leaky bung, a rusty drum, a rainstorm, a careless handler. Vickery's system addressed each risk. It created checkpoints where fuel was tested. It provided tools to remove contamination. It trained people to recognize problems. It standardized procedures so that every base operated the same way. The impact was measurable. In November 1943, when Vickery arrived at Guadalcanal, the contamination rate was 37%. By April 1944, it was 2%. By the summer of 1945, it was below 1%. Engine failure rates dropped proportionally. Sortie rates increased. Aircraft availability improved. The air campaign accelerated. The strategic consequences were significant. The Pacific War was an air war. Control of the skies determined control of the seas and the land. American aircraft carriers launched strikes against Japanese bases. Land-based bombers attacked supply convoys. Fighters escorted transports and provided close air support. Every mission depended on reliable engines, and reliable engines depended on clean fuel. Vickery's work enabled the island-hopping campaign. As American forces advanced across the Pacific, they established airfields on captured islands. These airfields became bases for further strikes. The Japanese were isolated, their garrisons cut off from resupply. The strategy worked because American aircraft could fly sustained operations, and they could fly sustained operations because the fuel was clean. The B-29 campaign against Japan was another example. The B-29 Superfortress was the most advanced bomber of the war. It had pressurized cabins, remote-controlled gun turrets, and powerful engines. But those engines were finicky. They ran hot and required high-quality fuel. Contamination caused engine fires and failures. The 20th Air Force lost aircraft to fuel problems in the early months of the campaign. Vickery's intervention changed that. He provided filtration units and test kits to the bases at Saipan, Tinian, and Guam. He trained Army Air Forces personnel in his methods. The contamination rate dropped. Engine reliability improved. The B-29s flew longer missions with fewer aborts. The firebombing of Japanese cities and the final atomic strikes were made possible, in part, by clean fuel. Vickery's system also had a human dimension. He understood that quality control depended on people, not just equipment. He built a network of trained fuel handlers who took ownership of the problem. He gave them the tools and knowledge they needed. He trusted them to make decisions, and they responded with professionalism and dedication. One of Vickery's students was Petty Officer First Class Eugene Morrow, a mechanic from Texas. Morrow had worked on aircraft engines before the war. He understood how sensitive they were to fuel quality. When Vickery trained him in fuel testing, Morrow became a zealot. He tested every drum that came through his depot. He filtered fuel that looked even slightly suspicious. He rejected shipments that did not meet standards. His commanding officer complained that Morrow was slowing down operations. But Morrow's squadron had 0 engine failures due to fuel contamination. The complaints stopped. Another graduate was Chief Petty Officer William Kowalski, a supply specialist from Chicago. Kowalski had no background in chemistry or engineering, but he learned Vickery's methods and applied them with precision. He set up a fuel quality control station at Ulithi, one of the largest forward bases in the Pacific. He trained a team of 6 sailors. Together, they tested and filtered thousands of gallons of fuel every day. Kowalski's station became a model for other bases. Vickery visited Ulithi in early 1945 and praised Kowalski's work in a report to Admiral Nimitz. These men and hundreds like them were the backbone of Vickery's system. They were not engineers or scientists. They were mechanics, supply clerks, and laborers. But they learned to see fuel as more than a commodity. They saw it as a critical component of the war effort. They took pride in their role, and they saved lives. Vickery's legacy extended beyond the Pacific War. After the war, the Navy incorporated his methods into its standard operating procedures. The Fuel Quality Control Manual he wrote became the basis for training programs at supply schools. The filtration units he designed were refined and mass-produced. The field test kits were improved and distributed to bases around the world. The commercial aviation industry also adopted Vickery's principles. Airlines recognized that fuel contamination was a safety risk. They implemented testing and filtration systems similar to those Vickery had developed. Refineries adopted quality control standards. Fuel handling became a specialized field, with trained personnel and standardized procedures. Vickery's influence can still be seen today. Modern fuel quality control systems use advanced technology, electronic sensors, automated filtration, and real-time monitoring. But the underlying principles are the same. Test the fuel, remove contaminants, train the personnel, standardize the procedures. These are the lessons Vickery taught in 1943 and 1944. The story of Howard Vickery is also a story about the nature of military innovation. Vickery was not a high-ranking officer. He did not command fleets or divisions. He was a mid-level engineer with a specific problem to solve. But he had the technical expertise, the practical experience, and the determination to find a solution. He worked within the system, but he also challenged it. He pushed for changes that were not popular. He spent money that was not budgeted. He trained people who were not supposed to need training, and he succeeded because the results spoke for themselves. Vickery's work was also a testament to the importance of logistics in modern warfare. Armies march on their stomachs, the saying goes, but air forces fly on clean fuel. The most advanced aircraft, the best-trained pilots, and the most brilliant tactics are useless if the fuel is contaminated. Vickery understood this. He saw the problem that others overlooked, and he fixed it. In the end, Howard Vickery's contribution to the Pacific War was quiet but profound. He did not win battles in the traditional sense. He did not sink enemy ships or capture territory, but he enabled those who did. He turned fuel from a liability into an asset. He built a system that worked across vast distances and harsh conditions. He trained people to maintain that system, and he did it all with limited resources, no precedent, and a clear sense of purpose. The pilots who flew from Henderson Field, the crews who bombed Tokyo, the squadrons that cleared the skies over the Philippines, they all benefited from Vickery's work. Most of them never knew his name, but they flew on the fuel he made clean. They trusted the engines he made reliable. They came home because the systems he built worked. That is the legacy of Howard Vickery. Not glory or recognition, but results. Not headlines, but lives saved. Not monuments, but a system that endured. In the vast machinery of war, he was a single engineer who saw a problem and solved it. And in solving it, he changed the course of the Pacific Campaign.